This will give you the best learning outcome instead of just let me go through it once, right? And then because this is a homework 7, because this is homework 9, it's due, I think, next Friday, along with another one, the start block. So start from here. So the 3 questions you want to answer for D flip-flop. First, is it able to set and reset? Second, is it a D flip-flop passing D to Q? Third, if it's rising edge triggered. If it is rising edge triggered, this is still the third question. Okay. If it is rising edge triggered, is it synchronous or asynchronous D flip-flop? Okay. Whenever the rising edge arrives, is the data being sent to Q or is waiting for the falling edge? And we want a synchronous one. Okay, is this one, can this one do set and reset? First question, yes. How? Yeah, why? Because 0 here, this is on, it's gonna pull this up to VDD, and I got a 1 here and 0 here. So you give a 0 to reset, you got a 0 for Q. And it's called 0 active because 0 will trigger that reset. And we want a 0 to trigger set as well, so we need a NMOS transistor and an inverter, because whenever S is 0 or S bar is 0, the input here is 0, it's also 0 active. I want to trigger setting, the setting mode. So when this is 0, after the inverter is 1 here, so it's going to turn on this NMOS and pull this down to ground. So I got a 0 here and 1 here. So whenever S bar is 0, it's being set. 0 active, yep. So the one thing you need to know, because if you build a circuit, this is one of the homework assignments, I just want to let you know, if you build a circuit, it may not work for the set and reset, because if you use a normal transistor width, it probably won't work. So you need a stronger PMOS and NMOS to make it work, including the inverter. Inverter or not? Inverter probably is fine, but for these pull up and pull down transistors, you need them to be strong in order to to make it happen here, because there are so many other caps, parasitic capacitance being. We haven't learned that yet, but starting from next week, we're going to cover that digital models. You'll see the gate has a capacitance. So there are so many of these charges being stored in the input-output of the transistors. So you need a pretty strong, it's just one PMOS to compete with all these other transistors, or to charge up all these transistors. So you need a strong transistor. How to make a strong transistor? To make it wider. Because according to the square law equation, it's W over L, right? For a stronger transistor, you need a W to be bigger. So it's going to be a big transistor here, like wider. So if you think about the layout, a wider transistor means it's longer or wider. It's just a trap. I know you are going to jump into it. I just still ask. So during the layout, you have the rail-to-rail, right? You have the transistor in the middle. So for a wider transistor, is it going to be longer or wider? Longer. So the channel, yeah. So the poly is in the middle, right? Yeah. So the length is crossing the poly is the length, because that's the way the holes are migrating, right? It's across the poly, which is the length. So the width is this.
Yeah.
Remember?
Yeah, that. It's easy to think about. The width is that way. The width is that.
Yeah.
What? Yeah. Because
the channel is a poly. That's a channel. Yeah. Got it? All right. So it is able to do set and reset, no problem, if you add something else over here, right? And the second question is, if this is a D flip-flop, let's see. So for the rising edge, For the rising edge,
It doesn't pass, we don't know.
okay, so it's being clocked, right? It's being clocked. So before the rising edge is a zero logic for the clock. So 0 means this one will be a wire, is a PMOS. So can't figure out which one's PMOS, which one's NMOS. Okay. Yes. Yes. Okay. So right before the rising edge, clock 0, right? So this is on, it's passing. So the whole thing here is nothing but inverter, right? Okay. So right before that rising edge is an inverter. So the D is the input. So this must be D bar or D naught. Okay. And before the rising edge, this is off, the NMOS. And before the rising edge, this is on. Okay. Because this is off, so it's not competing with the PMOS whenever this is on. You know what I mean? You don't want to like one is pulling it down, one is pulling it up, then it's competing. It's gonna, you can say it's shorting part of the ground. It's bad. So you have to make one off when the other one is on, right? So right before the rising edge, this was on, this was off, right? So because this was on, it is able to pull this up to VDD. Okay, the other way to say it is this point is being charged up by VDD. So this is a logic 1, right before the rising edge. You're saying, hey, it's pulling it down as well. No, it's not. No matter what this is, it can be on, can be off, doesn't matter. This is off. Okay, so it's cut the wire, any connection from the ground to this joint, to this wire here. Okay, so this will be charged up to VDD. Any questions? No. Okay. D bar and 1. Okay. So when the rising edge arrives, what's going to happen? This will be off, and this will be on, right? So this will be on, but this will be off. So it's going to block. So depends on what the voltage here is, right? This can be on, can be off. All right. If this is on, which means this is 1. Okay, 1 on. It's going to discharge this point to ground. Whatever charge is stored in there will be discharged to the ground. So this becomes 0. If you have a 1 here, this will be 0. It's being inverted.
If you're building a circuit practically, would you have to put like a capacitor or something there to hold that charge?
There are old charges around the transistors. You don't need, yeah, it's going to be hold here, and you don't need to hold it for forever. It's just a floating one, and you want to discharge it whenever you have to. So these ones will be adequate to do that job, right? If this was 1, right, like I said, if this was 1, when the rising edge arrives, this will be on. It's going to pull this point down to ground. So if this was 1, after the rising edge or right at the rising edge, this becomes 0. Okay? When this is 0, if this was 0, what's going to happen? The 1 will stay there, will be held there, because this is off, and this will be off as well at the rising edge. So this will remain unchanged. All right. So if this is 1, you got a 0. If it's 0, you got a 1. So it's being inverted always.
So you're just inverting.
Yeah, inverted again, right? So D bar just becomes D. Okay. At the rising edge, this becomes a wire, so this becomes an inverter. So D will be inverted once and twice. So D bar and D. Yeah. So D will be transferred to Q eventually at the rising edge. Make sense? So it is a D flip-flop. You'll figure out after you do it yourself. You'll figure out you do need something here to control it. Multiple rising edges? No, just one rising edge. Just one rising edge. We're just talking about one rising edge. So D bar will be so D naught will stay here, right? So whenever rising edge arrives, this one becomes D very quickly. And then this after rising edge, this is 1, right? So it's a combinational logic because it's not being clocked. It's gonna after this point, Q will become D with a very minimum delay. Just the 2 delays of the two inverters, right? Any other questions for?
What's the point of having that clock in the middle there?
Here?
Yeah. Well, right, but like, couldn't you just take it out?
Yeah.
Then how do you set and reset it?
Oh.
Why would that have any effect on the set or reset?
Yeah.
You have to set and reset it, right?
Yeah.
Yeah,
How do you
separate signals, right?
Hmm?
The set's a different signal than the clock.
So for example, if you don't have these two, right, but only have set and reset being shorted to this point, could you do that?
Would it not hold the value of
So the first stage is like loading D naught in, this block is 0, then rising edge hits, passes D into the next stage, through that stage, inverts at 0, inverts at 1, inverts because it's 1, and then inverts twice. No, just one more.
So this one.
What's the other?
You need a rising edge to trigger it. If there's no rising edge, it won't pass to here. So whenever clock is 0, this will be, oh yeah, because when clock is 0, this will be always 1, right?
Oh,
It won't store it.
I see.
Yeah, it's going to be affected by this transistor. You need something to block the.
So if we didn't have that, it'd be like
It will be always 1 whenever the rising edge after rising edge or right at the falling edge, this one will becomes 1 immediately.
oh, okay.
Yeah, if you got it here, when the rising edge arrives, the inverter is being turned off because this guy blocked the path to here.
Why could you not just have D going through a single NMOS where where the gate is clocked? Why would that not?
It was past D naught, then. Or signal.
You need a rising edge. It cannot be. It's going to be a level trigger. You need an edge trigger, but not level trigger. Now let's take a look at this structure again. See why it's rising edge trigger, but not level trigger, right? If we got after the rising edge, the clock signal becomes high for a certain amount of time, right? So whenever clock's high, if D becomes D naught, are we getting a D naught here during the logic high without the edge?
Not gonna pass. It
Mm-hmm.
just won't pass through the first stage. Right?
Mm-hmm. Let's see. Let's go through it. Don't just guess. Okay.
Because if it's still a 1, then it won't pass.
It's a 1 here, right? So it's going to turn
everywhere. Right?
It's 1 everywhere. Yes. Yeah, it won't pass here, right?
We're at the beginning.
It passes at the beginning. At the beginning, it just becomes an inverter when clock is 1.
Mm-hmm.
I thought when the clock is 0, it passed.
No. Wait.
Yeah.
Oh,
It won't invert it.
Let's make some examples. What about that? 101, for example, right? If we just want to see if Q will hold at D whenever D changes, right? Because whenever clock's high, if D changes, we don't want Q to change. That's why it's rising edge trigger, but not level trigger, right? So if D becomes D naught, Is it going to change? Clock's high, blocked. Could you tell? I mean, you couldn't tell. So let's do 0, 1, 0 first. For example, if D is 0. If D is 0, clock is 1, right? So 0 will be here. It's still 1. It stays at 1. Yeah, clock's 1, so this is blocked. 0 is here, 0 is here, 1 is here, but it's not going to affect the point here, voltage here. It was D naught, it's still D naught because it's not changing anything, right? It just shut down this transistor, but it's still going to hold the voltage here. Yeah. So 0 will be 1 here because it was 1. It's still 1. It's not going to be changed. If this is 1, this will be on. This is on. This becomes 0, right? So 0 and this will be on. We got 1 and 0, right?
Go back to the last.
This one?
Yeah, that.
Yeah, because this PMOS is on, right? But this is off. Even though this is on, it doesn't matter because this is off.
How does it pass VDD?
Which one?
Wait, no, it doesn't pass VDD. VDD just turns off.
Because this is on at 1.
Yeah.
Right, so it's just ground.
No, because it was debarred, remember?
0.
Yeah, no. We went through because the clock was a 0 before the rising edge.
I thought we were just
Yeah, but it was. I mean, before the rising edge, it was 1. After the rising edge, this becomes a wire. It passes D to D bar, so this becomes D bar.
We're passing 0 through at the rising edge. Then it turns.
Yes, that's.
It blocks the NMOS. It turns off the inverter. Before the rising edge, it was a logic 0, which activate the inverters. That's why it's D and D bar, right?
Yeah.
We're not changing D right now, okay?
No, the clock is just rising edge.
Yeah.
Going through it with zeros and ones instead of D bar, so that we can go through it with 1 afterwards, without changing the clock back down to 0.
Yeah.
To see that if it changes
Okay.
during the class.
We went through the D and D bar things and it worked, right? Remember? So after this one becomes voltage high, the inverter is off. It's not inverting anything anymore. So if D was 0, for example, it's still 0 right now, okay? So D will still be D bar since it was D bar and now it's just turning off this one. It's going to hold the charge here. It's not going to change anything. There's no path to short this one to anywhere else because this one is off. This one is off again. It was 1. It will be 1 in the future. Make sense? What I mean? So before the rising edge, it make it into 1. And after the rising edge, just turn off everything. It's going to be a floating 1. Just floating VDD. It's charging up all the caps. So 1 here, this is on. This is on because after the rising edge, the clock is on, right? So this one will be put down to 0, right? This becomes 0. It's not competing with this one because this one is off. So logic 1 will turn off the PMOS. So this point will be discharged to ground. So this becomes 0. Because this is 0, so this PMOS is on, so this point is being put up to VDD, and then 0. Okay, so 0, 0, no problem. However, if we change this one to 1, whenever the clock is still high, still not arriving at that falling edge yet. After rising edge, it's still on the logic high. So just want to verify if we change D, if D, the data is changed during that logic high, are we going to change Q or not? If it's changed, which means it's a level trigger. If it's not changed, it's holding the charge. It's a rising edge trigger. If this becomes 1, what's going to happen? Clock is still on, right? Clock still on. What's going to happen? No, clock, yeah, this is still,
Everything becomes closed on
nothing changed. It's still 0, right?
that. That second one's like
Nothing's changed. Make sense?
Like Mason's
It is.
Is it rising edge triggered?
Is it synchronous or asynchronous?
Oh yeah.
It is, since when we are looking at the rising edge, D becomes Q
It
immediately.
doesn't have to flip back.
You are not waiting for the falling edge, remember? We haven't arrived at falling edge yet. We're still at the rising edge. Just slow it down, right? Rising edge and then logic high. It's not being changed.
Are we all working together or are we all working both
What
of
are we
these?
presenting?
We'll see how that works, all right? So that was 0, 1, 0. What about 1, 0, 1 at the very beginning? If D was 1, oh, it was 1 at the very beginning, right? At the rising edge, what happens at the rising edge? So if this was 1, the clock, when the clock was low, this must be inverted, right? Because it's D bar, always D bar, D bar, right? No problem. So 1, it should be 0. Before the rising edge, right? So when a rising edge arrives, what's going to happen? Because this is 1, so it's going to holding, it's going to keep this on, right? Even though this is off after the rising edge, this one will be turned on, will be always on. So this is still 0, it's not changing anything, still 0. So this is still 0, then this one was on before the rising edge. This is 0, you just ignore it because this is off. It cut everything off. So this will be 1. This was 1 and still be 1, right? And before the rising edge, there's nothing. And after the rising edge, this is on. So inverter is going to invert it. D, right? Look at the second one.
Oh, I can't tell. You go first.
First, can we standard reset this D flip-flop? Okay. How do we do it? So if you give a 0, hey, let's see. If we give a 0 here, right, since you see a bar on the top, which means it's 0 active. If you give a 0 here, a 0 will be sent to here, right? And you got a 1, no problem for Q. But are you getting a 0 at the same time here? Whenever we just give a 0 here, but this one should be 1. 1, right? So this is not changing anything, right? So 0, you got a 1 here, and 1 will be fed into this NAND gate. And because we are not resetting it, so this should be 1. Okay. So now we got a 1, 1. We need another 1 to make a 0 here.
It comes out of that second, or that first NAND state that goes into.
Let's do this. So clock, because it's being clocked, right? So before the rising edge, or it doesn't matter when, or when we are looking at it, after it's parted up, it's going to oscillate, start oscillating. So when during the 0 phase, it's going to kill this two NAND gate and give it 1, 1 here. That's working as the initial state. Because whenever you got a 0 for the clock, it's going to kill this two NAND gate and give it 2 1s. That's the initial state. So you got 1, 1, 1, you got a 0, right? So what about reset? Put a 0 here, you got a 0 here, definitely, no problem, right? So 0 will be fed into here. Wait, reset. Oh, get a 1. You got a 1. The 1 will be fed into here. Works the same way, right? Got 3 1s. I got a 0, right? So set and reset works, no problem. What about D? At the rising edge, are we sending D to Q? And why? So D is here, right? At the rising edge, clock is being treated as a 1, a very short period of time. So we got a 1 here. D here. So now setting and resetting, so this must be 1. And right before the rising edge, the clock, the voltage low of the clock kills all the NAND gates, give you an initial state of 1, right? So 1 will be fed into here. So you got a 1 0 1. What's the result here? Oh, 1 D1, 1 D1. Yeah, D bar will be fed into here, right? And 1 will be here. So 1 1 D bar here will be okay. What about the other one? So D bar, because this is the same wire, right? 1 1 D, rising edge 1, reset 1. So at the rising edge, change the 2 1s to D bar and D. But whenever the falling edge arrives, it's going to reset these 2 points to 1 1. So like 1 1 D bar D, 1 1 D bar D, like that. Okay. But we're still not arriving Q yet. How do we determine that? So no problem here. Set is not setting anything, right? So this is 1, right? Not resetting anything, so this is 1. No problem. What about the other input? So we need these 2 inputs. Let's give examples. If this was 0 1 at some point before we change the data, okay? If it was 0 1, where should you start with? Keep in mind, start with 0. Start with 0 because 0 will give you a definitive answer here. So 0 comes here, will give you a 1. And 1 will be fed back here, right? So 1 1 D bar are going to give a D. Oh, D. Yeah, D 1 D bar 1, right? So it's going to be a D. So Q is D. Good. What about Q bar? So D will be fed back here. DD1 will give a D bar, right? No problem. So what if it was 1 0? Still start with 0. 0 will kill the NAND gate, will give you a 1 here, right? 1 fed into here. And 1 D1 will give you a D bar. And D bar come back here. 1 D bar 1 D. Yeah, tiny. Yeah, a little bit, but it's fast. It happens fast, so we'll correct itself really quickly. Won't be a huge glitch. Right? Is that stable? Why? Because D bar come back here, right? D bar will be fed into here. You got a D bar 1. So D bar and the D bar is still D bar. Being inverted, it got a D. So D comes here, D1, still D bar. D bar, so stable. Okay. So it is a D flip-flop. Is this rising edge triggered?
Can we start on a do?
I see why you dropped it like 7 feet now.
Is rising edge triggered? So whenever it's stabilized at logic high here, right? Okay, so it's not at edge anymore. It's stable logic 1 for clock. And if D flips, so D becomes D bar now, and we want to see if this still D is still D bar, okay? That's the only thing we want to verify. So this becomes D bar, which means Yeah, this is 1. This was D. So keep in mind, D bar D at the rising edge. At the falling edge, 1, 1. At the rising edge, D bar D. And after the rising edge, this is what we are talking about right now. That was right before the logic high. I was on the edge. This was changed to D bar D. Okay? So D bar, D bar 0, 1. 1. D bar. Clock is 1. D. Stable. What about the other one? D 1, 1 here, 1 here. Right? D bar here, D bar here. 1 here. 1, 1 D bar, D. D. 1. 1. D 1, 1 D bar. D bar, D bar. D bar here, D here. Make sense?
Easy. What is rising edge trigger?
Rising edge trigger.
Is this one? No, this one's a
Yes.
we don't need the rising edge trigger.
I use this one for the first version of the EDC. Worked really well. It worked. And this one is the one we use for the senior side. It worked also.
Yeah, why did you use this one? Has a lot more transistors than the top one.
Yeah. Yeah. So we should use this one. I think. Yeah. Haven't seen any disadvantage yet. All right. So I'll give you 10 minutes to go through it by yourself. I think that will be the only way to have a best outcome. I don't want you just listen to me, but just go through it by yourself.